Hello physics enthusiasts, welcome back to our series on Landau and Lifshitz's course of theoretical physics. Today we're tackling Chapter 1, Section 2, the principle of least action, or Hamilton's principle. It's a cornerstone of classical mechanics, and we're going to explore it with some technical math. So let's start unraveling this fundamental principle. The principle of least action says that every mechanical system follows a path where a certain quantity, called the action, is minimized. This action is calculated using a function called the Lagrangian, which we denote as L. The Lagrangian is a formula that includes the system's generalized coordinates, their velocities, and time. Let's get into the math behind this principle. The action, which we denote as S, is a crucial concept here. It's defined as the integral of the Lagrangian over time. The principle of least action tells us that the actual path a system takes is the one where this action integral S is minimized, or more generally extremized. In other words, out of all possible paths the system could take between times t1 and t2, it chooses the path that makes the value of this integral as small as possible. This idea of minimizing of the action integral is a fundamental aspect of how physical systems behave. How do we find this path? We consider slight variations in the path, represented mathematically by delta q, ensuring these variations are zero at the start and end times. We then look at how these variations change the action, denoted by delta s. The change in action, denoted as delta s, arises from the first-order variations of the Lagrangian L. This equation represents the fundamental idea of how small changes in the system's path affect the total action. Now, to find the specific path that makes delta s equal to zero, a condition necessary for the action to be at an extremum, we apply integration by parts on the term involving delta q dot. The reason we seek delta s equals zero is rooted in calculus, similar to finding maxima or minima of a function. In essence, for a function to be at a maximum or minimum, its first derivative must be zero. Continuing with our derivation, after performing integration by parts, we are left with an integral expression and a boundary term. Due to the specified boundary conditions, delta q of t1 equals delta q of t2 equals 0, the boundary term vanishes. This leaves us with an integral that must equal 0 for all values of delta q. This leads us to Lagrange's equations. The derivative with respect to t of the partial derivative of L with respect to q dot I minus the partial derivative of L with respect to qi equals 0. These equations form the backbone of classical mechanics, describing the system's motion. These equations are powerful. They show how the motion of a system is completely determined by its Lagrangian. The beauty of this principle is its universality. It applies to a vast range of physical systems. Let us look at some intriguing properties of the Lagrangian, which deepen our understanding of its role in physics. First up, Lagrange's equations. They form a set of second-order differential equations. In practical terms, this means the motion of our system is described by equations that need initial conditions, like where everything is and how fast it's moving, to predict future behavior. Next, consider a system made of parts that don't affect each other, like two separate mechanisms in a machine. Surprisingly, the Lagrangian of the whole system is just the sum of the Lagrangians of each part. This additivity makes analyzing complex systems much more manageable. Another key point is about scaling the Lagrangian. If we multiply it by any constant, the equations of motion remain unaffected. This property gives us the freedom to adjust the Lagrangian to suit our needs without changing the physical outcome. And here is a particularly subtle yet powerful aspect. You can add to the Lagrangian the rate of change over time of some function, and it still describes the same physics. This means two different-looking Lagrangians can actually represent the same physical reality. To summarize our exploration of the principle of least action, from the variational principle, we derived Lagrange's equations by minimizing the action integral S. We learned about the additivity of the Lagrangian in systems that don't interact. Moreover, the Lagrangian is defined up to an additive total time derivative. And that concludes our journey through the principle of least action. It's fascinating how such a simple idea can explain so much about the physical world. Stay tuned for more episodes where we delve deeper into the textbook of Landau Lifshitz. Don't forget to like, subscribe, and share your thoughts in the comments.